I just want to let you know, so this lab, you have all the data. You do need to do the graph and you do need to do the analysis, not right now. So put the lab away, okay? I want that lab before spring break. Does that make sense? Because I don't want it to be like hanging over your head over spring break. So I just need it, well, so that would be what, not tomorrow, but Friday, okay? It should be doable. It should not be a like long, arduous process. Just that sheet, hand it to me on Friday. If you are feeling industrious and get it done tonight and want to give it to me tomorrow, that's fine too, okay? So let me just write this down so that everybody is clear that the lab is due when? Friday. That'll give me something fun to do over spring break, right? All right, so questions on that? Nope. Fabulous. All right, we are going to talk about another principle of waves. This one is the last part that we're going to talk about from chapter 25, but it really could fit in chapter 26. So we're kind of moving into chapter 26. We talked about what waves were and some of the little, definitional pieces about them. We talked about standing waves, and you looked at standing waves today. The thing that we're going to talk about today in particular is called the Doppler effect. How many of you have heard of the Doppler effect? Anybody? A few of you? Cool. Does anybody know what it is? Or can you think of an example of it?
Like when you hear like the motorcycle rooming away, it just sounds like quieter. It's like
No, you're very close, but there's like I was totally with you, and then you said this one word, and I was like, oh, kind of close. So here's the thing, is that there are two principles at play. So we're talking mostly about sound waves for the moment, okay? We're talking about sound waves. If I stand right here and I sing a note, you hear it, right? If I walk to the other side of the building and open the doors so you can hear it kind of, and I sing the same note, it's going to sound like the same note. Are you with me there? Yep. But it's going to be what? Quieter. It's going to have less amplitude, less energy. Are you with me there? Okay. So if you have proximity, or how close or far away we're talking, that impacts the volume. Okay? And the thing I want you to know about that is that is not the Doppler effect. The Doppler effect is not about volume. Okay? Until she said quieter, I was totally on board with what Magda was saying, though. So give me the situation that you were just talking about before.
Like when the motorcycle rooms away.
When it rooms away. So let's imagine that you're standing on the sidewalk, and there's a motorcycle. Let's say that it's vrooming towards you and then vrooming away from you. Is that okay? Yo.
Is this the thing like if in the movies, like when you're close to a car and they slam the door, it sounds like it's at the same time, but when it's far away, you can see it slam before you hear it?
No, this is not. That's a different thing, and we'll get there later. So it's not volume. It's not how loud it is, and it's also not like when it happens. It has to do with what it sounds like. Yeah, it goes mew. That mew. That is the Doppler effect. I don't know how to spell that. Mew. But that's what it is. Okay? The Doppler effect is. Okay. So follow along with that if you want to. The thing that I want you to know about the Doppler effect is that it is a change in the perceived frequency of a wave. Now, we haven't really talked about what frequency means, except that it's the number of cycles per second, right? For a sound wave, frequency leads to pitch. Okay? The higher the frequency, the higher the pitch. So those of you that are musically inclined among us, Okay? Know that as you go up the scale, right? We're getting higher and higher in pitch. The reason that that happens is because the frequency of that note is increasing. Okay? We're gonna see how that works tomorrow. We're gonna spend a lot of time tomorrow talking about sound. Okay? But what I want you to know right now is just that pitch, the thing that, right? That high-low, that pitch has to do with the frequency. How are we doing? Are we okay so far? Yeah? Okay. I'm going to start a little video mostly because the guy that did the video draws pictures better than I do. But I'm going to pause it throughout. We probably won't get through the whole thing today. Does that make sense? But we're going to take notes from the video because it'll be, like I said, more efficient than me trying to draw pictures for the rest of the hour. So I need to make sure that my sound is on loud so you can hear it too. You can. This guy talks a little bit fast, but I will pause it as I go. So here we go. I'll be all the way back. There we go. Okay.
The Doppler effect. In Sheldon's words, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Got that? That is from Big Bang Theory. Yes. Yes. Anybody seen that episode? He dresses up for Halloween as the Doppler effect because why wouldn't you, right? Yeah. I'm going to play that one more time because it's kind of funny and it does kind of make sense. So it says the apparent change in the frequency, that's what we just talked about, right? Change in the frequency of a wave caused by, I'll go back and find out what he actually said again.
Sheldon's words, it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Okay. It's the motion between the source of the wave. So what's making the noise? In Magda's example, it was that motorcycle, right? Okay. And who's the observer? Yeah, whoever's standing there. Yeah. So what is he doing? He's got these little lines. He looks kind of like a zebra with different size stripes, right? So this is the source, and the lines there are like the waves going out from him. Okay, that's what's going on in that costume. It's a little bit silly and a little bit goofy and pretty darn nerdy. All right, so now he's going to explain what that is.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this.
Okay, so far so good? Can you imagine that? So when you had the slinky, you were sending waves just in one direction, but now we're talking about something that emits waves in all directions. Generally, waves are emitted in all directions unless you have something specific like a string that you're sending them down. Okay, so that would be one thing to know. One thing to know is that you've got waves that are going out, out, out. Here we go.
We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it, they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency.
I'm gonna pause that for a second. Are you understanding what he's saying? He talks fast and with that, British or whatever accent, so it's kind of hard to make out what's going on. But so these lines, right, are the frequency, right? How often does it happen? Does that make sense? How many times per second? So if you watch here, these things are going to hit really hard, really fast. Whereas if the eye was back here, would they be coming as fast? No. So the frequency as it's moving towards is higher. The frequency as it's moving away is lower. He's going to do it right now.
And if the object is moving away from a stationary observer, the waves are observed at a lower frequency.
How are we doing? Are we okay there?
So that is the Doppler effect, the apparent change in the frequency.
I'll put that up there so you can write it down. If you want, again, you don't have to write this all down word for word, not at least for me. But the Doppler effect is the apparent change, and the key word there is apparent. The actual frequency is not changing. Okay, the actual frequency is the same. The apparent change in the frequency of a wave that's caused by relative motion between the source and the observer. Is that making sense so far? All right. Ornery child. Okay, I'm gonna go ahead and click ahead. I will put this, I'll link to this up on Canvas as well, so you can watch it again if you
Of a
want.
wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you. And a car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on?
Okay, I wanted to look at the notes because the notes are pretty, there we go. Okay, so are you with them there? Okay, so if you do this, my second teaching job, I had the opportunity to drive by railroad tracks every single morning on my way to school. Like I was driving like parallel to the railroad tracks, and literally every morning a train would go by me and it would honk its horn, like because I was like almost to this town, and so I got to hear the Doppler effect like every single morning. It's like, this is great physics teacher life right here. Okay, so as it's coming up, it's got this high note, and it gets louder and louder because it's getting closer and closer, but it's the high note, high, and then right there it goes low. Okay. Does it actually go high and low? No, if you're in the car, I'm not advocating that you drive around North Liberty, lay it on your horn. Okay, I want to make that clear. But if you happen to be like Janelle and you just lay it on your horn while you're driving around, does it change the note ever? No, it's just like, right, that whole time. But if Carly was standing on the side of the road and Janelle laid on her horn, it's going to go, no, right? It's going to go high, low. Even though to Janelle, it's just going to be this middle note, and it's the note right in the middle between the two is the note that actually it has. Mm-hmm. Yeah.
I don't even remember those notes.
It's okay. I'm not going to quiz you on that part.
No. As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency.
High
Which
frequency,
you
high
interpret
pitch.
as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects.
How are we doing? Is that making sense to you? Yeah? So right now, if you haven't yet written this down, because you didn't actually like write it down, I want to make sure that it makes sense to you. You want to write down now, okay? That as a source of waves, so you could say a car or a motorcycle or whatever, approaches, as it gets closer to you, tell me about the pitch. It's going to be high. And it doesn't change. It's going to be one note that is higher than the source. Are you with me there? So it's not like going, right? It's one note. Okay, you with me there? One note high, one note low. And then it just gets quieter and louder.
So as a source of wave.
As the source of the waves gets closer to you or approaches you, the pitch or the frequency that you hear is higher than the source frequency. Okay? Go ahead.
So if the frequency is higher, would that mean that amplitude would be higher, or would it?
No, amplitude is related to volume.
So as a source of wave,
The frequency is higher. I wouldn't say goes, is higher. And as a source of waves, goes away, travels away from you, the frequency, the perceived frequency or the frequency you hear is lower than the source frequency. So the hardest part about Doppler effect, you guys, is separating pitch and volume, right? So amplitude is related to volume. Frequency is related to pitch. You might want to write that down too. That's a good thing to know. Amplitude is related to volume. Frequency is related to pitch. I'll write that down too. The example that he just gave is not my favorite example of Doppler effect. My favorite example is the next one that he's going to do. And we've got just a couple minutes, so we're going to let him do it right now. This is the stuff I think is just crazy cool. So here we go. The other kind of Doppler effect.
Another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch. So what does it mean for light?
Okay, I'm going to look at that in just a second. Stars move. Did you know this?
Yes.
Stars move. They don't move, like we don't perceive them as moving really fast. They're actually moving really fast. Like everything really is moving pretty fast in the universe. But stars move relative to us all the time. Not a lot. It's not like they're hurtling towards us in that, they're not going to like hit us, okay? But they do move towards us and they emit waves, right? They emit light. And so that light's going to get bunched up, which means it has a higher or lower frequency up here. Higher. If you had a star that was moving away, it would be seen at a lower frequency. So now he's going to tell us what's going to happen with light. We have not gotten to light yet. We will get there soon, okay? After spring break in a couple days, we will get there. But I want you to just be exposed to this and see it because you're going to need it in a minute anyway.
Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color.
Have you seen that before? Have you seen the spectrum before? I saw it every day when I walked in. Yes, you have. Okay? Instead of pitch, last thing I want you to write down real quick. Frequency for light. So, you wrote frequency leads to pitch. We can also write frequency leads to color. Okay? Frequency leads to color. I'm going to start with this tomorrow. There is a question on this on your homework, and I think you can get it if you think hard about it, okay? Think hard. You can do it. All of your homework is about the Doppler effect, so hopefully that makes sense. And, you could read the stuff, too, in the book. The book is helpful, so I would recommend that you do that, all right? I will get some more homework assigned for you by tomorrow so that you know what is happening in Chapter 26, because we're going to start Chapter 26 tomorrow. Woo! It's going to be good, you guys. And your lab is due when again? Friday. So don't forget about that. We don't want to miss it.